Hello viewers, welcome to my channel Connect Civilian. So in this lecture we will see how to design a eccentric rectangular footing with biaxial moment. That is, moment is applied in both the direction, that is in x direction as well as in y direction. Okay, so if you will see the moment, so the moment in x direction will be like this, moment in x direction, and the moment in y direction will be like this. Okay, moment in y direction. So both the moment is applied, that's why it is called biaxial moment. Okay, so we have already done the uniaxial moment. If you haven't checked my video, please go to the playlist and check my video. I will provide the video in the end of the description. Okay, so these are the data that was given, so we are going to consider the same data with biaxial moment. Okay, as the size of the footing was 430 by 230 mm. Okay, it is mm, 430 mm by 230 mm, and the SBC of soil was 250 kN per meter square. Service load is 550. So this service load is dead load plus live load. Okay, don't be confused how service load is calculated. If you use software for the design of the building, then the service load is the dead load plus live load. Okay, and it was combined in the design procedure. When you get the result for the reaction and the total load from the STAD or ETAB, whichever software you are using for building design. Okay, so grade of concrete of column is M20 and the grade of concrete for footing was M25, and the moment in x direction is 100 kN meter and the moment in y direction is 50 kN meter, and the grade of steel here we are choosing Fe 500. Okay, so these are data that was given. Now we will find the size of the footing first. Okay, so for that we have to assume the self weight of the footing. So here we are taking the self weight of the footing as 12%. Total load including self weight of the footing will be 550, that is service load plus 12% of the service load. Okay, that will come as 616 kilonewton. Why we have taken the 12%? So you can take between 10 to 15%. So for safer side I am going with the 12%. You can also check with 10%, but after the designing the footing you have to cross check whether the load on the footing was coming is more than that is the self weight of the footing that was coming after the designing was more or less than we have assumed, that is 12% of footing. Okay, so it will always be less than our sorry, more than our calculated area. I will show you at the end of the video how it was calculated. So we have already done in uniaxial moment rectangular footing, you can check from there also. Okay, so here the area of footing will came as 616 kilonewton divided by 250, and 250 the SBC of the soil. So area will come as 2.46 meter square for now. Okay, and we have to also check the maximum ultimate net upward pressure for the both the direction, maximum net upward pressure and minimum net upward pressure. After that we will select the size of the footing. Okay, to consider the length of the footing, I am going to consider it as 2.5 is the length and the width of the footing was 2 meter. Okay, so and mx is 100 kilonewton meter, so your ultimate moment will be 100 into 1.5, that is 25 kilonewton meter. Similarly my was 50 kilonewton meter. I will add it here, kilonewton meter, and your ultimate moment in y direction is 50 multiplied by 1.5, that will come as 75 kilonewton meter. And the section modulus for x direction will be PL square by 6. So P is the width, that was 2, and L is the length, that was 2.5. So 2 multiplied by 2.5 to the power whole square divided by 6, that will come as 2.08 meter cube. Similarly for y direction we have to calculate, but the formula will differ. It is LP square by 6, so it will come as 2.5 multiplied by 2 to the power whole square divided by 6. Okay, it will come as 1.67. Now our P by A ratio will be, service load divided by area will be 550 by 5. Okay, the area of 2.5 into 2 will be 5. Okay, so it will come as 110 kilonewton per meter square, and mx by mz will be 150 divided by 2.08, that was section modulus for x direction. It will come as 72 kilonewton per meter square, and for my by zy will be 50 by 1.67, and that is section modulus in y direction, and it will come as 30 kilonewton per meter square. So your net maximum upper pressure and minimum upper pressure will be, maximum will be P by A plus mx by mz plus my by zy. Okay, so it will come as 110 plus 72 plus 30 is equal to 188 kilonewton per meter square. So we have already calculated in Excel sheet also. Here see 188 kilonewton per meter square. So I will provide this Excel sheet also. You can download and also design from this using the Excel sheet only. Similarly, your P minimum will be P by A minus mx divided by zx minus my divided by zy. So it will come as 32, and your P max should always be less than your SPC, and your P minimum which should always be greater than 0. Okay, so here I forgot to mention, your column was at the center, but due to the moment in x and y direction, your CG of the column will change. Okay, so it will come nearby this position. Okay, so your footing CG will come here. If your footing CG will come at the center, this. Okay, so due to the moment, your column CG will shifted to this position. Okay, to here. So that's why it is called eccentric footing. Okay, here. Okay, CG of column, and it should always be less than L by 6. Only then the formula will be applied for P max and P minimum. Okay, always remember it should always be less than L by 6. So our eccentricity, if you see the eccentricity, it will come for x direction, it will come as 182. How eccentricity will calculated, I will mention here. uh, Eccentricity will be equal to, sorry, equal to m moment by p. Okay, the moment is 100, that is moment in x direction, divided by your service load, that is 550. So it will come as how much, 182 mm. Okay, and it is less than L by 6, that is 417 mm. Okay, so this eccentricity is for x direction. Similarly, you can calculate the eccentricity for y direction. Okay, so it should always be less than our L by 6, and and for y direction you have to calculate with the same formula. All you need to do, you have to change the moment only, that is 50 in place of 100 you have to put 50 divided by 550, so it will come as 91 mm, which is less than L by 6 for y direction, which is coming as 333 mm. If you divide by 6, so it will come as 333 mm. Okay, so it is 2 meter, so you have to multiply it with 1000. So 2000 divided by 6, so it will come as 333 mm, which is greater than our calculated eccentricity for y direction, that is 91 mm. So that will be also okay. So further we will go. So here we have calculated the P max and P minimum also here. Now we will choose the size of the footing. We have already chosen size of the footing is 2.5 and 2 meter, and after choosing the size of the footing, all the checks will be okay here, so we are going with the same size. If these checks will not be okay, so we have to again increase the size of the footing. Okay, so now it was okay, so we will go for bending moment calculation. So for first we will go for x direction. Okay, so the net upward pressure, so x direction is your longer side. Okay, now the net upward pressure for x direction will be 62 kilonewton, and your that is P by A minus mx by mz. If you put this formula, P by A is 110, okay, and minus mx by zx will be 72. So if you subtract 110 minus 72, it will come as 62 kilonewton per meter square. Similarly, P max you can calculate, that is P by A plus mx by zx. So this is formula used for x direction. Okay, so you have to add the 110 plus 72, so it will come as 158 kilonewton per meter square. Similarly, for y direction you have to calculate. So for y direction, your P minimum will P by A minus my by zy. So P by A is 110 and my by zy is 30 kilonewton. So it will come as 80 kilonewton per meter square. Similarly, P max will be P by A plus my by zy. So it will come as 140 kilonewton per meter square. So we have find the net upper pressure for both the direction, that is for x and y, and the P minimum and the P maximum value, and our critical phase will come at the face of the column. Okay, so here we have to find the net upper pressure also for the bending moment calculation, because you at the face of the column here your bending moment will be maximum, because pressure will be more here than the starting. Okay, so we have to calculate the uh, net upper pressure at the critical phase, that is at 1.465 meter away from the x direction, and similarly for the y direction, that is 1.115 meter away from one phase. Okay, so length of the critical phase for x direction will come as 2500 by 2, so it will come at the center of the column, minus 430 by 2, so it will come as 1035 mm. Similarly for y direction, it is 2000 by 2 divided by 230, that is the column size, by 2, so it will come as 885. This is 885 and this will be 1035. Okay, 1035. Now net upward pressure will be at the critical phase, that is at the face of the column will be calculated like this, and by interpolation you have to calculate the value for net upper pressure at the critical phase. So at starting we will consider it at 0. So at 0 our net upper pressure is 62 for x direction, 62, and at 2.5 it is 158. So at 1.465 we have to calculate. Okay, that is at the face of the column. So at 1.465 it will be px is equal to 158. So I have written in interpolation. How we will do the interpolation, we have written on that method only. So it will be 158 plus 158 by minus 62 divided by 2.5 minus 0 multiply by 1.465 minus 0. So it will come as 118.25 kilonewton per meter square. So your P net upper pressure at critical phase for x direction will be 182.25 kilonewton per meter square. Similarly, for the y direction we have to calculate the net upper pressure. Okay, so your maximum net upper pressure at critical phase will become here, and in similar way you have to do, that is at 0 it is 80, at 2 that is at starting it will be 0, it will be 2. Okay, so at 2 it is 140. So at 1.115 from here to here, okay, it is 1.115. So it will come as 113.45 kilonewton per meter square. You can do the interpolation by the same method. So moment in x direction will be calculated, and the formula will be force into perpendicular distance. So we will divide into two triangles for x direction, for y direction. So from that triangle you can calculate. So first force for the first triangle will be half, base will be 118.256, this will be base, and this will be taken as height, that is the pressure, net upper pressure at critical phase. So half into 118.256 multiplied by 1.035. Okay, so and it will act at the CG of the triangle. So it will be at 1 by third. Okay, so it will be at 1.035 divided by 3, and your width of the footing is 2 meter, so multiplied by 2. Okay, so it will come as 42 kilonewton per, sorry, kilonewton meter. And for the second triangle you have to also do the same procedure, that is half, base it is 158 multiply by 1.035 multiply without the footing, that is 2 meter, multiply by CG of that is at 2 by third of the triangle. So it is 2 by third of 1.035. So it will come as 113 kilonewton meter. So total moment for x direction will come as 42 plus 113, it will be 155 kilonewton meter. So your ultimate bonding moment in x direction will be 1.5 into 155, that is 233 kilonewton meter. Similarly, you have to calculate for the y direction. So this will be first triangle, this will be second triangle, and it will come as half, net upper pressure will be here. So it is 13.45 multiplied by 0.885 multiplied by the width of the footing, that is for y direction it is 2.5. I will write here 2.5 meter. Okay, and it will act at the CG of the triangle, that is at 1/3 of the 0.885. So it will come at 37 kilonewton meter. Similarly for second triangle you have to calculate 1 by 2 half multiply by 140 multiply by 0.885 multiply by 2.5 multiply by 2 by third of the triangle, that is 0.2 by third of 0.885. So it will come as 91 kilonewton meter. So total moment will be 97 plus 90, 37 plus 91, it will be 128 and your ultimate moment in y direction is 1.5 multiplied by 128 is equal to 193 kilonewton meter. So here we have find the moment at both the direction in x and in y. So you can just follow the maximum moment for the calculation of reinforcement and depth if you want, but for more economical design you can calculate for both the values for x and y direction with the given moment for different directions. Okay, by using the given moment for different direction you can find. Okay, or you can just directly go with the maximum moment if you want. So here we have done for both the moments, so you can easily understand what is happening. So the next step will be calculation of the depth of the footing. Okay, so for FE 500 we have taken the grade of steel as 500. So we for SP16 you can check it was for FE 500 your formula will be MUX is equal to 0.133 FCK BD square. So you have to use the code for these formulas. Okay, from SP16 you can get these formulas, or you can directly use this Excel sheet, so you don't have to use any uh, codes for that change of the formula. It will automatically change by itself here. Okay, whatever grade you want to choose, just choose the grade and the value will change automatically. Okay, so your MUX is equal to 0.133 FCK BD square. So MUX in x direction it is moment in x direction it is 233 multiplied with 10 to power 6 for the conversion is equal to 0.133 into 25, that is the grade of concrete for the footing, multiplied by width of the footing, that is 2000 multiplied by the effective depth, that is d square. So we will find that d, we will substitute that d to the next side, and by using the all the values we can calculate the effective depth for x direction, that is 233 multiplied 10 to the power 6 divided by 0.13. So it is 0.133, sorry, 133 into 25 into 2000. So our effective depth for x direction will be calculated as 187 mm. Similarly for y direction you have to calculate, you have to use the moment in for y direction, and by putting all the value you can get the effective depth for y direction also, that is coming at 152. So we have to use the higher values to get pass for the one way and two way check. Okay, so we have just double these values, so you have to double these values. If it is coming 187, so at least you can choose the overall depth, so that your effective depth will be more than 350 mm. Okay, so that will also be safe for one way and two way check, otherwise will not going to pass two way check and one way check, that is punching check. Okay, so we are going with the effective depth, sorry, the total depth as 500 mm. Here we are choosing cover will be 50 mm, die of the first layer of bar will be 12 mm, and die of the second layer of ball will be also 12 mm. Okay, so first layer will be in x direction and the second layer will be in y direction. So first layer will be parallel to x direction and second layer will be parallel to y direction. Okay, it will be look like this. Okay, so in next lecture we will see how to calculate the reinforcement and go for one way and two way check. Okay, so if you like this video please subscribe to my channel. Thank you.